We're going to kind of recap the theorems that are associated with the AP Calculus AB class, and we'll do some practice problems that look very, very much like the free response questions you're going to see on the AP exam. So let's recap with our theorems here. First of all, we have the intermediate value theorem, which says we've got to be continuous. And if I know that the y values, like one's above and one's below a certain y value, then I can guarantee that there's going to be a y value that hits that particular y value on the interval from A to B. I know that's a lot of words, but a lot of times what we see this applied to is this. If I know that there's a y value down here, and I know that there's a y value up here, and I know the function's continuous, then the function can do all kinds of crazy stuff, but I know at some point it's going to hit a y value in between. That's really what the intermediate value theorem says. And a lot of times it's applied to guarantee us that there's a zero, that there's a value that hits the y value of 0. Okay, then we've got the extreme value theorem. The extreme value theorem says if we're continuous on an interval, then there's got to be an absolute max and min. That absolute max and min can happen at critical points. That's like our normal hills and valleys in the graph, or it can happen at our endpoints. And I'll link the video above that I did on extreme value, so you can go back and watch that if you need a refresher on how to find the absolute maxes and mins. Then we had Rolle's theorem. Rolle's theorem told us that if we're continuous and differentiable and the y values at our endpoints are equal, then we're guaranteed to have a derivative equal to 0 somewhere on the interval. Now remember, Rolle's theorem was just a specific case of the mean value theorem. So when we looked at the mean value theorem, we saw a little bit more broad application here. But the key with Rolle's theorem is you got to be continuous, you got to be differentiable, and those y values have to be equal to each other in order to apply Rolle's theorem. And then finally, we looked at mean value theorem, which looks very much like Rolle's theorem in its prerequisites. So it's got to be continuous, you got to be differentiable, but you don't have to guarantee that the y values are equal. And then we get this beautiful formula, which I see actually required more often than not on the AP exam. Now remember, if you saw one of my previous videos, you know that I refer to this as the slope calculus way equals the slope algebra way, because this really is our y2 minus y1 over x2 minus x1. If you remember your slope formula from algebra, that's really where that's coming from. So I refer to it as the slope calculus way equals the slope algebra way. Another way might be the slope of the tangent line equals the slope of the secant line. So as we look at these free response questions in this video, I want you to really focus on which of these theorems can we apply and why. Okay, so look at this problem. We're given the rate at which water flows out of a pipe. It's given as a differentiable function, and we've got the table showing us the rate every 3 hours for a 24-hour period. We're asked to estimate the value of r prime at 5 and explain what this means. So remember, we're being asked to estimate. We're not being asked to give it exactly. So we don't know the derivative, right? We can't do the derivative at 5. So the next best thing to the slope of the tangent line would be to do the slope of the secant line. So I'm using approximate here with the squiggly lines because it's not going to be exact, but I'm going to do the slope. If I can't do the slope calculus way, the next best thing would be the slope the algebra way. And so I'm going to do it the slope around the point 5. So I'm going to do it from between 3 and 6 here. Notice I did y2 minus y1 over x2 minus x1. That's really what I did here. So r of 6 is going to be 10.8. And r of 3 is 10.4 over 6 minus 3, which is 3. So on top, I've got 0.4 divided by 3. Now, friends, I even I look at that and go, "Oh, what am I supposed to do?" So I'm going to clear the decimal just to make it a little easier. I'm going to multiply by 10 on top and bottom. Then it makes it a little easier for me to reduce. Okay. Now, this is the derivative of R. So I need units. This is gallons per hour on top over hours on bottom. So it's gallons per hour, or, oh, not equals, gallons per hour squared. Gallons per hour, or gallons per hour squared. Then they want an explanation as to what does this mean in this problem? So let's explain it like this. Since the value is positive, and it is, the rate of water flowing out of the pipe is increasing. The rate that the water is flowing out is increasing. And we need to be very specific at t equals 5. That explains what this is actually telling us about the problem itself, about the rate at which the water is flowing out. All right. So look at B then. Using correct units of measurement, find the average rate of change. Ooh, that we know that terminology, right? From t equals 3 to t equals 18. So average rate of change, this is where we're doing slope of the secant line, right? This is where we're doing the slope algebra way. So let's go to our chart. At 18, the R value is 10.7. At 3, the R value is 10.4. And then I've got 18 minus 3, which is 15. So I've got 0.3 divided by 15. Multiply by 10 again, friends. I've got 3 over 150, or 1/50th. And again, they wanted correct units of measure. So this is gallons per hour over hours, or gallons per hour squared. All right, now C says, is there some time between 0 and 24 where the derivative equals 0? Justify your answer. Now notice it didn't ask you to find the place where the derivative equals 0. It simply asks you, is there guaranteed value? Now that's going to be speaking to one of those theorems that we're looking for. Now remember, the one that equals 0 is Rolle's theorem. So go through your criteria. Since R of t is continuous and differentiable, on 0 to 24. And remember, the third condition for Rolle's theorem is that the y values are equal. So R of 0 equals R of 24. Then Rolle's theorem guarantees a value of t, and I'm going to use t here instead of c, on the interval from 0 to 24, such that R prime of t equals 0. Okay, all of that is necessary for the justify your answer part. Now do you see how they're not going to say use Rolle's theorem to da 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 da. You're going to have to recall those theorems. And I think that page that we did right before this one that has all of the different theorems on it, is a great page to keep in your notes. Keep it handy so that you can refer back to it. Okay, let's do one more here. And we've got the total order and transportation costs measured in dollars for bottles of Pepsi Cola is approximated by this function, where X is the size order size and number of bottles, answer the questions. So is there a guaranteed value of R on the interval from 0 to 3 such that the average rate of change is equal to R C prime of R? Now remember, we're not being asked to find the value, we're just asking is it guaranteed? And so when we're looking at the average rate of costs equal to the derivative, that's mean value theorem. So let's go through our criteria for mean value theorem. Mean value theorem says we got to be continuous from 0 to 3. Now my problem right here is with the continuous would be at 0 and at 3. And then I look at my criteria for the mean value theorem. So mean value theorem said we had to be continuous on the closed interval. So I'm going to say since C prime of x is not continuous at x equals 0, mean value theorem does not apply. Or guarantee a value of R so that C prime of R equals the average rate of change. So that's where I'm just saying how it doesn't apply, okay? Because it's not continuous at that endpoint. Okay, now it's saying, is there a value on the interval from 3 to 6? Now we change the interval, okay? So are we continuous from 3 to 6? We were not continuous at 0. We were not continuous at -3. We also weren't differentiable there because we weren't continuous. So this is going to be a yes, since C of x is continuous on 3 to 6 and differentiable on 3 to 6 open interval. That's important. There is guaranteed a value of R such that, oh, this one's equal to 0. Okay, hold on. So this is going with Rolle's theorem. So I got to check that, right? I was going along mean value theorem here. So let's figure this out. So now if I'm continuous and I'm differentiable, we're good, but I've got to check those y values. So let's check C of 3 and C of 6. C of 3 would be 10,000 over 1/3 plus 3/6. So let's see, 5/6, so 10,000 times 5/6. I'll reduce that here in a minute. Let's do C of 6 now. That's 10,000 1/6 plus 6/9. 10,000, let's see, 18, right? Common denominator. 12 and 3 is 15/18, which is 5/6. So yes, we're good. So let's add, since C of x is continuous and differentiable, and C of 3 equals C of 6. There we go. There is guaranteed a value of R such that C prime of R equals 0 on 3 is less than or equal to R is less than or equal to 6. Okay, so did you see how I picked out if it was talking about Rolle's theorem or mean value theorem? It was based on what it was equal to. If C prime is equal to the average rate of change, that's talking about mean value. C prime is equal to 0, it's talking about Rolle's theorem. So I hope that helps with the theorems here. I'll do one more video with a few more examples. So I hope that helps. Bye for now.